So we're looking at page 23. So let's flip over to page 23 here. And in this case, again, now it's not just about reactions. When you talk about these things, when you talk about equilibrium, again, keep in mind that it's also about solubilities. So we can work the same basic process here. So when you look at this first one, it says silver chloride. We have silver, it splits into the silver and the chloride ion. We have a KSP. That's our equilibrium expression here. So do the next one here, PB. So you do two things. One, you have to write the reaction out, and the reaction or the dissolution, write it out here. So in this case, we have PbCl2. I'm going to put my arrow going both ways. It's equilibrium. So I have the lead 2 ion plus the chloride ion, and I've got 2 of those chloride ions for every one of the lead ions, right? So when I write my equilibrium expression, I'm going to call it KSP because I can see that things are just dissolving here. Again, if I called it KEQ, that would be fine. But it's more specific to call it KSP. Products over reactants. So I have my products here. If I can write today. So I have Cl minus, and it's squared, times Pb plus 2. If you don't put the plus 2 in there, you're not going to get it. Divided by, am I going to put divided by PbCl2? No. Why not? It's a solid. It doesn't have a concentration at all. So that's it for that. You don't have to go any farther than that when you do this. So do 3 and 4. Write out the reaction or the dissolution, and then write out the solubility expression. The hydroxide ion stays. Typically, the polyatomic ions stay together in this. Are you getting stuck on separating them into ions? Yes or no? No? Okay, did you come up with something like this? Okay, keep in mind when you separate these, you have the iron and you have the hydroxide. Hydroxide, you should remember, is a -1, but remember, you can do the backwards crisscross method. So that means this 3 was up with the iron, and since there's no number, it's a 1. The 1 was up here. The first one's always positive, the second one's always negative. Same way with the calcium. This 3 came from up here. This 2 came from over here, yes? So that's how we get the ion charges. Also, we can say that, oh, there are 3 of the calcium ions. So this is +2 and this is -3. And there are 2 of the phosphate ions. Yes? Okay. And then again, it's products over reactants, but the reactants are solid, so we don't have to incorporate them. Okay, so look at number 5. Calculate the KSP of AgCl if the concentrations of the silver ion is 1.34 times 10 to the negative 5 molarity and the concentration of the chloride ion is 1.34 times 10 to the negative 5. We already have the equilibrium expression up here written down. Is this silver chloride? So I'm not going to write it again. I'm just going to use my equilibrium expression that's up here. And I've got the concentration of the silver times the concentration of the chloride, which is, lo and behold, the same thing. So I could just put that number squared, right? Our units of measurement don't cancel out. But again, K, equilibrium, has no units of measurement. Pop that into your calculator. Did you guys get 1.7 something or other? How many sig figs should we have? So 1.80 times 10 to the negative 10. This is a really low K, correct? So is this dissolving very well? No, it's not. As a matter of fact, when I have silver chloride, I hate it. It doesn't dissolve very well, and it's so bad that it actually breaks into silver and chlorine gas, to be honest. It does really bad. It'll coat the inside with a little bit of silver, but mainly, it doesn't do that a lot, but it does it just enough so where it coats the inside of the bottle, it's stained with silver. Not a perfect coating, but you can just see it stained in there. But yeah, it doesn't dissolve very well at all. Silver chloride, terrible to dissolve in it. Remember that all chlorides are soluble except for silver, mercury, and lead, right? So I have silver chloride, but it doesn't dissolve very well at all. Usually we have just a little tiny bit and it'll do that. Silver nitrate dissolves better, obviously, because it's a nitrate, but it doesn't dissolve very well either. It does an even more solid coating of silver on the inside. And guess what? It's expensive. Does that make sense? It's silver? Yeah? Okay. All right, so calculate the KSP of lead chloride if the concentration of lead is 0.0257 molar and the concentration of the chloride ions is 0.257 molar. Okay, so now we have lead chloride. And since we already have our equilibrium expression written, I'm not going to write it again. So I'm just going to plug my numbers in. The chloride ion, and it's squared, times the lead ion, and it's not squared. Uh-huh. So what'd you get? Yes? Okay, do 7 and 10. What happened to 8? Oh, I guess I didn't like 8 and 9, so I took them off. Sometimes I do that. I'm guessing that's what happened. You add the exponents when you're multiplying, right? Yeah. Oh, well, I did something wrong there. You got some really obnoxious numbers. Yeah. Times 10 to the negative 38 and times 10 to the negative 25. Yeah. So again, what does this tell us about our K, about the solubility? Yeah. So iron hydroxide, isn't it all hydroxides are insoluble except for a few? So the iron hydroxide and the calcium phosphate are both really insoluble. They're not going to dissolve much at all. A tiny amount will dissolve, and that's about it. What about the phosphates? Is it not on there?
It says it's not on there, but it says everything else.
Yeah. Are the hydroxides on there?
Yeah, hydroxides are insoluble
Yeah.
except for calcium.
Yeah. Yeah. So a lot of times what happens is you make a saturated solution, which means that you dissolve stuff in it until you see stuff down on the bottom. And usually in things that are insoluble like this is what you use. When we do our next lab, we'll do that next week, and we'll do the solubility product constant, and you'll figure this out by, yeah. So you'll figure this out by dissolving stuff, and you'll do this with a lab rather than just look at the numbers in the chart here. Okay, flip the page. Okay, now the same kind of thing, still the solubility, only we're going to use a rice table with it. So in this case, what's happening is we're not finding KEQ or KSP in this case. What we're doing is we're finding the concentrations of everything. So when you look at this first one, it says, okay, we're going to make a rice table. So we have our reaction written in. Make sure that the reaction is balanced. In this case, it's not a true reaction, right? It's just a solubility thing. So what do I need to add to this? Here's my dissolution. Yeah. So I've got how many NIs? One of the NIs, and how many OHs? Two of them. So I have one Ni plus 2 and 2 OH negatives. So always make sure that they have, or usually I would have you write out the reaction so you wouldn't have to check it like that. But in this case, this is what's happening here. So the first thing is write the when they say equation, equilibrium expression. That's how they're going to talk about it on the AP test. So write the equilibrium expression. So KSP and since we have our reaction here, again, if you don't write the little charges here, you don't get it right. Okay, so calculate the molar solubility of NiOH2 if the KSP is 2 times 10 to the negative 15. Okay, when it says the molar solubility right here, they want to know what's the concentration of each of the little things there, the molar solubility. What's X? Basically, they're asking you to calculate X. So if I have 1 mole of it, that's just 1 X, right? If I have 1 mole of it, what's the molar solubility? So molar solubility, 1 mole. Remember, our X is basically in terms of 1 mole. If we have 2X, that's 2 moles. If we have 3X, that's 3 moles, because that's what the coefficients tell you in the balanced equation, right? So in this case, if we have this balanced equation, we would have 2 moles of this, and we would have 1 mole of this. So when they're asking you molar solubility, they're saying, hey, tell me what X is. If I have 1 mole of it, what's X then? All right, so in this case, we need our initial concentrations. Well, what's our initial concentration? Well, first of all, this is a solid, right? Are solids in the equilibrium expression? Just put a big fat X through there. We don't have to write anything in that. It's not even in the equilibrium expression, right? So when you get to these KSP ones, the solid part, just cross it off. The next thing, we started out with 0, correct? 0 of them. We didn't have anything. It was all solid. We started out with 0. And then we had some change. We're going to add some number X. So the nickel ion is going to increase by some number x. The hydroxide ion is going to increase by some number 2x. So then at equilibrium, and sometimes I like to put a line here because this is where it's kind of all worked out here. This is going to be x and 2x. So write the equilibrium expression. We just did that right here. I know that said write the equation up there, but I don't care. Equilibrium expression, we already wrote that. And then solve for that. So I have my equilibrium expression. Let's plug our numbers in. So did they give us KSP? They did. They gave it to us right here. So 2 times 10 to the negative 15 equals Ni plus 2 is x times 2x squared. So isn't that 2x cubed? 2 times 1? Oh, no, it's squared. So if you have solve for x. So if you take this step by step, divide by 4 first. So sometimes you guys forget the algebra because you're not in physics or anything. So you've got 5 times 10 to the negative 16 equals x cubed. Isn't that, wouldn't that be 5 times 10 to the negative 6 raised to the 1/3 power? Yes? Yeah? And you can plug that into your calculator pretty easily too. So we can answer caret 1 divided by 3. So when you do that, if you get, let's see, 5 times 10 to the negative 16.
7.
Yeah.
7.94.
So if I have it cubed over on this side, for those of you guys who forgot how to do this, so if I have it cubed over on this side, then all it does is if you take the inverse of that and do it over here. So this number it's this number to the 1/3. 1/3. Yeah. So I can pop that in the calculator if you're forgetting how to do this. Let's see. Let me put it in parentheses just to be on the safe side. Caret, what is it? 1 divided by 3. I might have used too many parentheses, but we'll keep it there. Yeah. So how many sig figs?
2.
Yeah, I'm seeing 2. 2 sig figs. So 7.9 times 10 to the negative 6. Now, does it have a unit of measurement?
No.
This is not K. They gave us K up here with no units of measurement, right? But they're asking for molar solubility, so they're asking, typically it's going to be in molarity. Because look at this, you just found X right here. What's the concentration at equilibrium? So it's 7.9 times 10 to the negative 6 molar. Yes? Sometimes I've seen the problems where instead of molar solubility, it'll actually be they'll give you everything in moles. So it's not molarity, it's just going to be in moles. So every once in a while they do that too. I've seen that on the AP test. I don't think that they would count off for the unit of measurement. They don't say it, so I don't think it would be too much of a problem here. Is that very much? No. So we already know that the hydroxides are mostly insoluble, but there is some in there, correct? There is some there is some that's in there, so you don't, if you're drinking this, you're not drinking pure water, are you? You're drinking some. And depending upon the chemical, that could be enough to cause damage. So you always want to make sure, you're not, like, there's a reason we're not allowed to dump lead compounds down the drain. I mean, I have that little red bucket back there that we put some chemicals in. This is the reason. Even though they're mostly insoluble, almost all lead compounds are mostly insoluble, right? They don't dissolve in water, and you think, well, why do we have to do that, blah, blah, blah. Well, that's why. Because there is some, they all will be soluble to a tiny amount, and so that's why we don't want it in the water in there. And then if you add nitrates to the water, like, there's a nitrates. Nitrates are in urine, right? So if you add nitrates to it, that makes everything soluble. So let's say I put something that was kind of sludgy, milky looking, because it's not very soluble, right? It's like lead iodide or something like that, and I put it down the sink because I'm thinking, oh, well, it's not that big a deal. Well, what I have done is I've put solid lead iodide in there. Even though it was mixed in with water, it wasn't a clear solution. When I put that in there, I'm thinking, okay, well, yeah, you can see that's going to just sink to the bottom, blah, blah, blah. But then when it meets the sewer line, the rest of the sewer line where urine's in there, yes, where a lot of nitrates are in there, then what you have is, oh, yeah, now that lead has completely dissolved in the water in the form of lead nitrate, and you can't filter that out. You can't use a normal, typical filter and filter nitrates out. So if you have the little filter on your water spout at home, or you have one of those separate little filters where you can put water in and it'll filter it for you, the nitrates don't get filtered out. That's not good enough. So you really have to be careful about what you put in there. So they have to, when they have the water treatment plants out at the edge of town, they're doing some heavy-duty stuff to it. They're making sure that it's potable, it's drinkable for that. Okay, so next one. Calculate the molar solubility of silver bromide if the KSP is 5 times 10 to the negative 13. Notice, if it's totally soluble, if the K is greater than 1, we don't usually mess with that stuff. It's mostly soluble. You know stuff's going to be dissolved in there. You know the water's going to be contaminated. Everything's going to be in there, right? It's the stuff that's insoluble that we quote-unquote say are that we say are quote-unquote insoluble. Those are the ones that we're iffy about. Exactly how much does dissolve in there? Because if it's on our list and says, yeah, it's soluble, well, then we know it's there, right? And if the K is greater than 1, then we know it's going to be really soluble, so pretty much everything's there. Okay, so we have silver bromide. All the bromides are soluble except for silver, mercury, and lead. So the equation or the reaction would be AgBr. Ag is +1, Br is -1, right? And that's in solid form. And so we have the silver ion plus what? What's the bromide ion? Is that balanced? Yeah. Okay, so we have our reaction. What's the initial concentration? Okay, so look, this is a solid. What can I do? That's a solid. Solids are not a part of the equilibrium expression at all. Solids and pure liquids we can cross off. If water were in here, pure water in here, pure H2O, we can cross that off too. So what's our initial concentration of the silver and the bromide ions? 0. We started out with solid stuff, so we start out, they don't have any, there's nothing in the water. Change in concentration. Well, look at my coefficient here. It's a 1, and this is a 1. So I'm going to increase the amount of bromide by some factor X. I'm going to increase the amount of silver iodine ion by some factor X. I'm going to increase the amount of the bromine ion by some factor of X. So at equilibrium, this concentration is X, this concentration is X. So my molar concentration, if I have 1 mole of the substance, what's my molar concentration? That's what we're talking about here. So what's the equilibrium expression for this problem? Okay, you just got a point for that. And then plug your numbers in. KSP, what's KSP? They told us up here. Equal, and these are two x's, so it's really x squared, right? How many sig figs should we have? 2, so I've got 7.1 times 10 to the what? Okay, I do have a unit of measurement on this because we're finding the concentrations at equilibrium. So it should be what? Molarity. Okay, do number 3. See if you can do number 3. Okay, what'd you come up with? Okay, so 2.0 times 10 to the negative 10? Yeah? Anybody else? Where did you mess up? Did you get that one? Okay, so I still have some people that usually go iffy when it comes to the algebra for getting this. So look at this. If I show every step here, then I've got my equilibrium expression. I plug the numbers in. So I've got 4 times 10 to the negative 38 is equal to 27x to the 4th. Divide out your 27 first. Do the simple stuff first. And then you've got 1.48 times 10 to the negative 39 is equal to x to the 4th. That's the same if I want to solve for x. It's 1.48 times 10 to the negative 39 to the 1 over 4 to the 1/4. And when you plug that into your calculator, you get 1.96 times 10 to the negative 10, and that rounds to, so we have 2 sig figs, 2.0 times 10 to the negative 10. So if you look at that, for me, it helps me if I do the steps. For you, maybe you can skim through and not have to do the steps, and that's fine. But I always want to make sure, so, because I tend to drop negative signs everywhere, they get lost in the ether somewhere. I tend to lose digits someplace, so it helps me to make sure I'm going through all the steps of it. It just depends on what's going to work for you. But know yourself, know your weaknesses, know what works best for you. Okay, I'm going to leave number 4 here so you can go back and you can practice on this later on when you're studying for the test, yes? Okay, flip the page. Okay, so calculate KSP following the steps to write the equation and all that good stuff here. So calculate KSP if the solubility of nickel hydroxide is 3.95 times 10 to the negative 6 moles in 500 mils of pure water. Okay, so calculate the molarity of nickel hydroxide that dissolves. What they're saying is they didn't give us a liter of it. They're saying, hey, they gave us this many moles in half a liter. So calculate the molarity. That's what it's asking you. Molarity is moles over liters. They're going to do stuff like this. Remember, you've got several steps to those problems. They might do something like this. They're saying, hey, you have this much solid. What molarity is it? So before you can plug stuff in, you need to know the molarity that's going on here. So the molarity here is 3.95 times 10 to the negative 6 moles in 0.5 liters. So what's your molarity? Okay, what's our equation? Our chemical equation. So we've got nickel hydroxide, and it's NiOH2. It's going to dissolve in the water to a great extent or a little extent? Little. Look at this K. Where's our K here? Here's K. Nope, that's not K. Where's K? Did they give us K? Oh, calculate the KSP. All right. So we don't know the KSP just yet, so they're going to ask us about it. So what do we have? What's it going to split into? Nickel plus 2. Okay. If this is where you're having trouble, stop and talk to me after class, and I'll remind you. It's just a matter of remembering what you did before in your pre-AP, because it's really a pretty simple thing. So it's just going the backwards crisscross method to figure out what it is here. Okay, so what am I going to do with this first piece? It's solid. So I can cross it off because it's solid. The solids are never in our equilibrium expressions. I like to go ahead and write my equilibrium expression because it kind of helps me, kind of solidifies things, because if it's not in the equilibrium expression, then we don't have to even consider it over here. So it says write the equilibrium expression right here. So my KSP is equal to the nickel plus 2 concentration times the hydroxide ion concentration squared. Products over reactants, but our reactant is solid, so I don't have to do that. How much nickel and how much nickel ion and hydroxide ion do we start with? 0. 0 here. So I'm going to add X here, so plus some number X. And since we have 2 of the hydroxide ions, it'll be twice as much as that. So we're going to have plus some number 2X. Okay, do we have the equilibrium concentration? We calculated the molarity right here. So for X, we have 7.9 times 10 to the negative 6 molar. What's for the hydroxide ion? Yeah, it's times 2 of that, yes? They gave us the molar solubility. They say calculate the KSP if the solubility of this is this many moles in 500 mils of water. So that's what they're talking about. They're giving us, this is like telling us the molar solubility. So this phrase right here is the molar solubility. They're telling us X. Whereas they asked us to find it in the last one, now they're telling us what it is. They're telling us the molar solubility. So this is what it is at equilibrium. So that's why we can put this number here. So 2X would be 1.58 times 10 to the negative 5 molar. Now plug it into your number, into your equation over here. KSP 7.9 times 10 to the negative 6 times 1.58 times 10 to the negative 5th squared, right? Don't forget the squared. So when they've given it to us in this situation, they've told us the solubility of it is this in 500 mils. So we can calculate that, convert that to a molarity. That's our molar solubility. So over here, they asked us to find the molar solubility. X, yes? On this page, on page 25, they gave it to us. And from that, we can calculate KSP. Can you see why this section is one of the ones that people have the most difficulty with? Yeah. This section, and then again, the next one will be acid and base equilibrium, so same kind of thing. Some of the stuff you're going to get like, okay, yeah, I can get the equilibrium expression. There's a point on there, absolutely. You can calculate molarity. The biggest thing that people find is that they get a little bit confused. They're thinking, wait, what did they give me to start off with? Always make that rice table. If you have an equilibrium problem, make a rice table. Even if you end up not needing it, it's going to make things clear and concise and organized for you to do this. Yes? 2 times x. Here's x, right? So 7.9 times 10 to the negative 6 times 2 is this number. Yeah? Okay, did you guys get what? Any unit of measurement? No. Okay, we're going to stop there. See if you can do number 2. It's done the same way. It's the exact same setup, exact same way. See if you can do number 2.